Hello everyone, it's December 20th. Alright, let's go for it. Hard problem. Maximum number of k divisible components. Okay, you're given the integer n and a 2D integer array edges of length n minus 1, where edges I is an edge between these two nodes. You are also given a zero indexed integer array of values of length n, where values I is the value associated with the ith node and an integer k. A valid split of the tree is obtained by removing any set of edges, possibly empty, from the tree such that the resulting components all have values that are divisible by k, where the value of a connected component is the sum of the values of its nodes, right, to the maximum number of components in any valid split. So this one, node 0. So these are the index, right? N nodes, n minus 1, yeah. Well, these are the index. I'm not sure if I like the way that it's expressed, because it's confusing, right? Because it's 1 values. So I might have to make some changes, right? So instead of, so we have the values 1, 8, 1, 4, 4, all right? So that's 0, 1, 2, 3, 4. So now it's 0, 2, so it's a 1, 1. Oh, because it can, okay, I see why it's this way. That's fine. So, all right, so 0 and 2, so it's 1. That's a 0, 1 and 2. A 0, 2, and a 1, 2. So this is going to be 1, which is going to be 8, and 1, 3. So this is going to be 3, which is 4, and 2 to 4. 2 to 4, so it's another one. It'll be 4. Right? This is like this. 1. Oh, they just set the indices. Huh. 0 to 2, 1 to 2, 1 to 3, 2 to 4. Oh yeah, I guess it's fine. And then you put the values in, right? You put the values in, and what you're asking is removing any set of edges. Right, we're removing any set of edges, so the remaining sum. So k is equal to 6. So right, so what we want is the value of a value that are divisible by k. So basically, value, well, can value be 0? Yeah, value can be 0. So basically in this case it is 0, 6, 12, 18, right? So if we see, these are the values. Oh, I have a 12. Oh, I have a 6. Right, I have a 6. So basically I want to, we have 240. 240. Wait, hold a second. I think it looks different. Damn. Let me redraw this. Alright, so we have 0 to 2, and then 1 to 2, and then 1 to 3, and 2 to 4. Okay, so 0 is 1, 1 is 8, 2 is 1, and both are 4. So we break here, right? So I have a 1, 1, 4, and an 8, 4. Yeah. Sum of values is divisible by k, so there's always going to be a way. Second example, 0 itself is 3, so I can break it out. We can say if we can find right, if you have a single node, then we definitely just break you out. Right? If it's a single node, we definitely break you out. We can also, we add everything together and see how many, what's the maximum number that we can get. I wonder, what if I turn it into 0, everybody? That'll be interesting. Everything is 0, so any combination will work. So it'll be 1, 2, 3, 4, 5. Yep. So you can break them up completely. Yeah, that makes sense. So yeah, because each component that you break off, the remaining is still divisible, so it's fine, right? So you can add them together. So this one, you add them together, it's 6 plus 12 is 18, right? 18. And the maximum is 3, unless you have zeros. If you don't have zeros, then yeah. Actually, if you can't even break all the zeros. It depends, because sometimes you break the zeros, the one that broken off doesn't work. That's also possible. So I don't know. You can start from a node, okay, and you just keep going until you hit k, right? You can say we start from any node. Now we go until we hit, then we break it off. And then, is that right? Yeah, because the sum of k is the smallest that you can break off, unless you have 0. In this case, we have a 0, right? This one is 0, but we cannot break it off. Actually, I don't know. What's this example? So it says 0, 2, 1, 6, 5, 4, 3. So if we fill them in, 0 is 3, 1 is 0, 2 is 6, 3 is 1, 4 is 5, 6 is 2. Oh, 4 is 5, 5 is 2, 6 is 1. And our k is equal to 3. So, if we pick anyone, so we say we pick here 1, and then 1 go to 6, that's 7, and then you go to 3, that's 10, that's 10, that's 15. So you say, okay, this one we get, but why do you not take this option? Because if I take this option, the remainder is not going to be divisible by 3. Huh. Interesting question. Can we like search from the? I don't know. Maybe we can. Wait. What if we sort this? If we sort this, then what we have is we have 1 at the position 3, 1 at position 6, 2 at position 5. Oh shoot! I forgot a 0. We have 0 at position 1, 2 at 5, and a 3 at 0, and 6, 0, and 2 at 2. Okay, so that's kind of sorted, right? 0, 1, 2. So what I'm asking is, for 0, can I just be by myself? So I look into here, and I say if 0 is by yourself, how do I see the consequence? Right? How do I see the consequence? So for 0, we know so we have to go through the whole thing. Usually I think, yeah, you go through the whole thing and then produce, let's just say produce a sum, right? So let's say we have a subtree sum, right, rooted in a node. Alright, 0, 1, 2, 3, 4, 5, 6. Sum is 1, 5, 2, and 1. This will be 3 plus that will be 9, and this will be 6. This will be 15, 18, right? So I say, because it's a 0, right, I can move it by itself. So if I move by itself, okay, if I move by itself, then we know it's children. Like everything gets broken off, right? So I have my parent. I know parent is 18. So if I broke off, I know this one has 12. So yeah, that's good, right? This one is good. And then because I need to break it by myself. So I have to cut the left, and then the left I see is only 5, and the right is only 1. So yeah, this is not gonna work. So 0 cannot be broken by itself, right? So if 0 cannot be broken by itself, so 0 must be with someone. So I check yeah, so like you have a node and you try to break. Yes, for each node you try to break away everybody that's attached to it and observe if you find the one that's already divisible, right? And you say, okay, I'm gonna try to break it away. So you break it away, you can see what's the subtree sum, right? You can see that. Okay. And then that you can tell if after you break away this current, whether the remaining will be good, right? If the remaining is good, that's kind of greedy, right? If the remaining is good, is that the best approach? We always find the smallest component and then try it. So would it be a case where the smallest component, now I say I just break it away, and then this will give me the most. But would it be possible that the smallest I don't break away, I keep it, right, with others? And I say if I keep it with others, then it will give me a better result. But if you keep it with others, because this one is divisible by k, so eventually it will always be better that you break this one off, right? It will always be better that you break this one off, unless this one, if it breaks off the remainder, is no good. But if it breaks off the remainder is no good, then you won't break off in the first place. So if you can break off, I think you should, right? I think you should. So you find one, and then you say I try to break. If it break off, then basically you reduce the complexity of the problem into small subtrees, right? But the problem now with a small subtree is everybody small subtrees over the parent. So you can just you can minus your number, so the parent will be fine, right? Your parent will be fine. Okay, and then you try to break. Okay, so in this case, let's say, 6, I cannot break this, right? I cannot break this. So that's a 0. So 0 cannot break. And then we have a 1, cannot break. Then we have a 3. So we try to break this. All right, okay, so I say I break this. When I break, this one's good, these two are good, so it's good. Now I try to break this, right? I try to break this. So if I try to break this, I look at myself, right? I look at myself, I am 6. So I say, okay, I can break it. But these are no good, so I cannot break it, right? I cannot break it. If I have a node that is divisible, but I cannot break, then what? That just means I have to keep all the nodes that's with me, right? And if you cannot break, then you move on to your children. how I would think. Yeah, you move on. You move on to your children, and then from your children, you do the same thing. You try to break the children. The children cannot be broken, so you cannot break the children. So you say, okay, don't break the children. But what if you can break the children? So you break the children, right? So you're saying we just stop breaking, we just try to break. Every node, we try to break it. If you can break, then you just break. And for the remaining, you try to do the same. It's the same thing. You start from any node, and you say, can I break? Can we try this? I mean, we know if we start from here, it will work, because this is a position 0, right? This is a 3. So we say, okay, this is divisible. I try to break. They are all good, so I'll break it. Now I look into here. And then this is a 6. I say, is this good? I try to break, but I can't. Because if I say break, this doesn't, so I cannot break. I move on here. This doesn't, so I cannot break. Move on here, cannot break. So once this is done, so this one will give me 1, right? And I come in here. This is a 0. I can break. I try to break, but these are no good, so I cannot break. So I cannot break now. So that's why it becomes here. Okay, so now it is very important that we kind of just swap the tree, right? Let's say instead of doing it this way, we will do it, we'll run the subtree sum. Let's say taking this is the root, right? So now we have is this, and then we have hold a second, I don't think it's the right way. So we have this coming down, we have this, that's a 6, this is a 2, right? And then this is a 3, and this is a 0, and then this is a 5, and this is a 1, right? So it's kind of like this, and we start from here, 1, 6, 2, 3, 0. So if we do the sums, this will be 5, this will be 1, right? So this is a 4, 3, this is not 0, this will be 6, right? This is a 1, this is 0, this will be 9, right? And then here this will be 2, so it's a 5, and this is 11 plus 17, and this will be 18, right? So that's a 2 and that's a 6. Okay, so yeah, this is kind of another way to get it. So again, I start from here, cannot break, go down here, right? This is a 6. Say try, can we break it? If I break it, this one's bad, so I cannot break. Coming here, it's a 2, cannot break. Coming here, that's a 3. Oh, we can try. We break it, then the before is, this is going to be 17 minus 9. -9. Oh, shoot. Yeah, like if I break, then the whole, Oh, what's the sum of this? Darn. Huh. How do we calculate the sum? So I know this is 17, so I break it, then this one will give me only 8, right? This one will give me 8. But the total of this thing is depending on this. Oh man. Can we solve this problem? So when we break, I mean, yes, I think we can, because I know the total, right? Total is 18. So if I break at any one, I know the remaining is be 18 minus 9. So the remaining is 9, right? This one will be 9. I know this one's 9. And because I'm the children, and as I go down, like I don't really care as I go down. If previously there are breaks, it's already done. So if I come to me and I can break, and I will break, then the previous must be by itself. So this will become by itself. So I break, and this I can compute. So because as I'm 9, this is 6. So if I break, yeah, if I break, this will be 6. So it's good. So I do it by itself. Now it's 6. So this might actually work, honestly. This might actually work. So essentially, what we do is we do a subtree sum, right? Subtree sum, and we do a subtree sum. So I know what the sum is, and I start traversing from any node. Doesn't matter, from any node, and as I traverse, I find a node that can be split. Then, well, actually, let's go to the first example. We actually haven't tried this in the first example. So in the first example, I have 1, right, 2, 4. This is a 0 and 3. So this is 1, 0, 1, 2, 4, and 4, right? So if I traverse, and k is equal to 6, okay, k equal to 6. Oh, k equal to 6, but I have to also do the sum. Right, so I have 4, 1, this is 6, this would be 4, 10 will be 18, right? So look at this, is 8, I cannot split, right? And then I go 4, cannot split, right? Go to here, there's a 1, cannot split. And then we have this problem, right? We cannot split. I think maybe what we can do is each one I'll just try to split. Regardless, I'll try to split. Right? At each node, I'll try to split it. Right? I'll split it and then I can have, so like it is 18, right? I can say I'll try to split here. It doesn't work. Split here works. So I'll just split here. Right, and try. So I can run this and then run this. Or I say I don't split. I don't split. So this node I don't split. What do you mean by you don't split? I think if you have a chance to split, you should split. Can we prove that? If you have a chance to split. If you have a chance to split, but you choose not to split, then you say this will give you more components, which means you don't split, those will become together, right? And the reason that you can split is because the remainders, they're all divisible. And you say, okay, I don't want to split. And eventually these things will become like together. You have a bigger one, right? And because you didn't split. And yeah, I think greedy might work. Just every time for each node, you just try to split. If you can split, just do it, right? You split it, and then like in this case, this one can split. So I split this, okay? Now once I split, it's going to be very interesting. Once I split, I will pass like this because it's children. So I just pass this one into, so this one can just by itself, we pass in the function. Now for me, right? For me, I lose this, so I need to update my sum, right? So this will be 12. Now I'll pass this to another one. Now once I pass this to another one, I start from here, and I say, okay, I have children, and I say I try to split. It does not work because of memorization. I already memorized starting from here, does not work. So what you're saying is you start from something, you start from any node, right? And then you just try to split. Alright, you just try to split. You split on one side and you see the results is good, then you try it. And you split on the other side, right? You split on one side. If it's good, then the good part you just start doing it, right? You can do it. And but what if you split on one side is good? So these two this is divisible and these two is also divisible. And if you split on the other, this is also good. Yeah, so exactly, right? Exactly, because it's a tree. I think it's a binary tree. They didn't say it's a binary tree, right? They say it's just a tree, but you only have n minus 1 edges length. So if it's n minus 1 edges length and it's a tree, I think it cannot. No, you can. You can. You can have this thing, right? Right, you can have this. But it doesn't matter. You start from any node. Oh yeah, it doesn't matter. Yeah. So it's I think n minus 1 edges just means it's going to be it's going to be a tree, right? It doesn't matter. You can start from here, right? And then we have 3, so we can say I split this, okay? Does this subtree good? If it's not good, we don't split. But it's good, then we do it, right? We do this, and then we pass this. Yeah, we just split once, and the remainder we just pass it down, right? That's one split. And you can also say, okay, how about I split here, right? We do this, right? And how about we split here? Now we do this. So exactly, that's exactly how we do it. And we will just, but the problem is you do different split. The tree itself is different, right? So I'm trying to see if we can memorize it, the state, right? But I feel like it's not as easy. I mean, when you split, they have a children. This is fine. You start from here as the root, right? It doesn't have a parent anymore. But once we split this one, we want to do this part, right? You basically remove a kid. Like how do you handle that? Right? You split out and then you say remaining we can try. Okay, here's the thing. Yeah, I'm just trying to see if, let's maybe make it simpler, right? I'd say if I cut here, then this will be good, this will also be good, okay? And if I cut here, this will also be good and this will be good. And then we kind of bifurcate, right? There are two paths. Can we reconcile this? Exactly, just like 0, right? Just like 0. Or are we saying we just only go with one path? We don't have to consider both paths. Let me think. If we say this can lead to the smallest. Yeah, well, when the way you prove is saying if you do this one way, you say, okay, this does not lead to the smallest, right? Because when these connected, when these two connected, it can give you a smallest. Okay, so that's actually what this is trying to say, right? You say if you cut here, then you won't get to the smallest. But you say, okay, so we say if you don't cut it, right? You group them actually together will give you a smallest. But we already know that if they cut it, the remaining is good. So eventually this will be cut, right? This will be cut. So yes, I think greedy will work. You just cut it once. Doesn't even matter. You just cut it once and then just keep going. Right? You just cut it once and keep going. So we pick whatever is a root and we'll cut its children, right? Left and right, doesn't matter. We'll cut it, and once we cut it, then we have two subtrees, right? Once we have two subtrees, and each subtree you run exactly the same, right? You run exactly the same. And you just say, okay, I'll cut it. If I cannot cut it, I'll move on to yeah, so for each node, right, I'll say, can I cut it? If I cannot cut, if I cut this, it's gonna, and then I just cut it. If I cannot cut it, I try the other one. I try the other side. What if I cannot cut on both? What if I cannot cut on both sides? Then what do I do? That's an interesting question. What if I cannot cut, right? What if I have this, I cut this, doesn't work. Okay, I cut this, let's say this side also doesn't work. Then basically you cannot cut. So you move on to this, and then you move on to here. Let me think. If you cut on both, doesn't work, what do I do? If you cut on both, doesn't work. So you move to here. I mean, let's say this one also has stuff. This one also has stuff. So basically, say here, what could because it's what could happen is the cut maybe happening here, right? Maybe you need to cut here, and then this entire thing, right? This is possible. So yeah, you come in here, and you start to check, and you don't check your parent, right? Because if it's gone, you don't check your parent. So you check here, and you cut, and you cut. If your cut is good, then you have then you have this, right? And it will keep updating the adjacency list, right? And then basically when you come in here, then this is the root, right? Basically the root is changed, so this is the root, and you say you cut here doesn't work, and you cut here doesn't work, then you go back. We have some repeated things here. What if that doesn't work? If it cannot be cut, that just means this node cannot be separated, so it has to be attached. Okay, and then when at a mat level, then I don't have to worry, right? I don't have to worry. I just starting from my side going down. Like I don't worry about this. I'm here. I just do the same job. I like if these two doesn't work, I don't care. Right? I just go down here and then return how many split they have. I return how many split they can have. Right? The subtree can be split. Give me like let's say 2 split. Is 2 split plus my split, right? So coming here, yeah, I only consider this. I am the root, and I just split. Can I do it? Can I do it? If nobody can do it. So for me, for my children, how many splits there are? And then this one basically no splits, so it's going to return 0. Right, this one will return 0. Will return 0, return 1. Because, if it's a split, then I'll say I can say +1, right? You can split out +1. Okay, so each split is just +1. Okay, so if this +1 and this split, you also +1, right? And then this split is +1. And eventually the answer is +1. Maybe it'll work. Maybe it'll work. Actually, I don't know if I want to implement it today. I'm hungry and then really not in the mood anymore. I think maybe I'll implement it tomorrow. Yeah, this one, like these days, hard problem takes 2 days to solve. I feel bad, but there's just no way for me to handle this anymore. But anyway, so how would you do this? I can do a vector. Yeah, I can do a vector, and then I can push them in, right? So basically, we can say a vector of int, right? We can call that a graph, and then actually we can also say graph n. Then we can say for auto edge of edges, okay, and then a we can say is edge 0, b is edge 1, okay, and then we say oh, actually I'm not sure how to initialize vector of vectors. How do I do it? Oh, you just push back. You just push back. think I can do default value. Hold on. Somebody downloaded something, I think. Yeah. I don't care too much. How can I make the second vector without size? Vector of vectors. Yeah, you push it back. You can do that. Okay. Can I say this? This? Oh, well, this might be working. And I can just say graph A dot pushback B. Graph B dot pushback A. Well, guess it will work. Okay, how big is n? It's not too big, so this one will work. All right, so this is to get that. Can I have a private int DFS? I have a root. We definitely need to pass the graph. Right, graph, we pass the root, we pass the graph. And, oof, graph. Yeah, it is graph. But I also need a, what do I need? I also need a thing called subtree sum. Right, I need a subtree sum as well. Okay, let's do the subtree sum. How do I do subtree sum? Jeez. Void get subtree sum. I have a node, don't call it root. It's just node. Okay. So, oh my goodness, I think it's the same thing. Okay. Alright, this one's easier to do. So we have a node, right? Oh, we also need parent, because I don't want to go back. Parent. I think this one requires parents as well, so we won't go backwards. Okay, so I'm at node. I'll put in the subtree sum, right? So I need to find, oh, this will probably will be easier if I do int. So I need the left subtree sum and the right subtree sum, right? And int sum, it's gonna be int, right? Everything can be int. Darn, 10 to the 9th. Jeez, just add another layer of complexity to this. Oh my god. My goodness. Value is 10 to the 9th, but we are adding them. Mod. Mod. You have to mod. Yeah, you add them and you mod. You minus, you can mod as well. Yeah, we have to mod. We have to mod, so we have to pass int k as well, right? So yeah, so I have sum, start with 0. Well, sum shall equal to we also need the values. Gordy monstrosity, what the hell is this? Values. This one doesn't require values. Yeah, this one doesn't require values. So s will equal to, maybe we can build on top of values. That is interesting. We probably can build on top of values. So we can say for int children of graph node, if children is not equal to parent, we do get subtree sum children. Actually, let me just delete everything. Children parent graph values. Okay. I believe we don't need this subtree sum. Right. So once it's done, after I hit this, right? Okay. Then what I'll get is values node is equal to values node plus values children, right? Mod. Okay. Now they might go out. Holy crap. Well, to prevent, I think I can do this. Well, they're already mod k, so this is they're smaller than k. Right? They're smaller than k. But still, I think it's possible. So, so I need to do is get a long. Right, so this is a long and mod k, and then I will return back to int. Right? And at the end, yep, that's about it. I don't have the return. So we do that. And we'll call it get subtree sum. Node is going to be 0, doesn't matter, whichever node, right? Parent, it's -1, and it's just gonna be graph, right? And then values. Okay. Okay, so that's that. Yeah, it's kind of late. I think what I'm gonna do is stop right here, and we'll keep going tomorrow. Try to implement it and see if it works. If it doesn't work, we'll check the result. We'll check the answer. All right, that will be it for today. Unfinished, but it's okay. We have some idea. We'll try tomorrow.